as we find ourselves getting ready for our next exam, it's not a bad idea to say, hey, what about some of these old exams? Because ideas tend to repeat themselves. So we have here a nice exam. This is Math 165, Calculus 1, our basic derivatives and integration. This was from fall 2022, 7 fun problems. Now exam 2 means that we're familiar with derivatives, and now we're getting into more of the advanced derivative techniques and, of course, applications. And, you know, it's nice to know that the things that we're doing can actually do things. So let's go ahead and work it out. And, of course, as always, since we want credit, we start by putting our name. And, well, we'll put our name here as answers, because that's what we're going to do. We're going to look at answers. Our first problem. Find the linearization of f of x, which is x cubed plus 1 to the 1/2 power at x equals 2, and use this to estimate f of 2.05. Now, you might say, okay, well, what does it mean to do linearization? And there's actually a big clue. The word linearization starts as line. And in fact, when we see linearization, we should really say, oh, this is really just a fancy way of saying tangent line. And a lot of Calculus 1, a lot of it says, hey, how do we think about this tangent line? Okay, so we could have rewritten this as find the tangent line of the function f of x at x equals 2. Now, what's the tangent line? Well, I like to say for a function, it would be f at a plus f prime at a times x minus a. So this is one way to write it, but it's the value of the function at your point plus the derivative at that point times x minus a. So we have our function, and all right, we have our f of x. We'll write it again, x cubed plus 1 to the 1/2 power. And notice they've already written it for us in a very calc-friendly way. So normally someone might write this as the square root of x cubed plus 1. But writing to the 1/2 power says, aha, calc-friendly. And calc-friendly in the notion that it's set up for our rules. So in this case, we have x cubed plus 1 is a function inside the 1/2, the square root. So chain rule. So the derivative looks like what? Well, the 1/2 comes down, x cubed plus 1, subtract 1, so it becomes negative a half, and then times by the derivative of the inside, in this case 3x squared. All right, so there's our function and our derivative. Now, these are not what goes there, because these should be numbers. So how do you get the numbers? Well, you evaluate. So, okay, what is f of 2? Well, that's 2 cubed plus 1 to the 1/2. Now, it turns out 2 cubed plus 1 is 9. Square root of 9 is 3. All right, so that's 3. What about f prime of 2? Well, that's 1/2. We have 2 cubed plus 1 to the minus a half times 3 times 2 squared. Now, 2 cubed plus 1 to the minus a half, well, it's the same thing here, except that the minus means it's really a 1/3. So really it's a half times a third times 3, and of course 2 squared means there's 2 2's. And we see that there's a 3 cancel, there's a 2 cancel, so we're left with a 2. All right, now we plug stuff in, right? So we say, okay, so our tangent line, y, looks like what? Well, it's f of a. Now a, this is the part here, this is our a. So f at a is 3. F prime of a is 2. So 3 plus 2, and then because we have a is 2, x minus 2. Now I like to leave my linearization in this form. Now you could expand, right? This says 2x, then minus 4 plus 3 makes minus 1. But when you're doing linearization, it's actually better to leave it in that form. Okay, so that's part of our answer. That's our linearization. But there's also the and part. and use this to estimate f of 2.05. And now we get into, well, what is linearization all about? It's a line, right? It is. It is a line. It's not just any line. It's somehow the line which is best approximating the function. So the idea here says really our function f of x is very close to 3 plus 2 times x minus 2, as long as we're close to 2. Now 2.05 you could argue is close to 2. So we could say, oh, f of 2.05, well, that's approximately 3 plus 2 times 2.05 minus 2. Well, okay, that's 3 plus 2. And here's why I like to leave it as x minus 2, because what we're really seeing is, what's the difference? How far did we move? And the answer is 0.05. And 2 times 0.05 is 0.1. Add that to 3, and we get 3.1. Good, good. And now we should note, of course, that f of 2.05, 3.1, should not be very far from f of 2. All right? If we had gone f of 2.05 is like 20, and f of 2 is 3, we'd be like, mistakes were made. But no, that seems a very reasonable answer. And there we go. One problem down. Tangent lines. We'll keep seeing that idea again and again in Calc 1. And so we should anticipate somewhere on this upcoming exam a tangent line is going to show up. It just might show up in a different name. Number 2. Let xy minus y squared equals 8. So this is a relationship between x and y. And it's a two-parter. Oh, they love two-part questions, don't they? Find dy dx, and then find an equation line for the tangent line at the point 6, 4. Okay, so let's do part A first. Find dy dx. Now, there's sort of two schools of thought. Now, one school of thought is to say, oh, I could try to solve for y, and you could do it here, kind of. You'd be mildly successful. Now, the reason I say mildly successful is that when you actually solve for y, you'll end up with a quadratic equation, and things can get a little bit messy. You'd actually get two different values, two different functions, if you will. And so it's not so clean. So it's not the right approach to try to solve for y. So what is the right approach? Well, the key here is to say, oh, if I don't have y as a function of x, but I have some relationship, it really means I have some implicit relationship. And when we see this, we say, oh, okay, so what we're going to think in our mind is we're going to say, okay, there is some function out there, y of x, we just don't know what it is. So when we're looking at this xy minus y squared equals 8, what we really, in our mind, all right, we really say, okay, this is x times y of x minus y of x quantity squared equals 8. We say, all right, let's take the derivative of both sides with respect to x. Because if two things are equal, the derivatives have to be equal. Say, all right, so let's take these derivatives. And now, say, all right, I have two things multiplying. So what's the derivative? Well, take the derivative of the first is 1 times y of x, we'll just write that as y, plus x times the derivative of y with respect to x. Now, it's not 0 because y is a function of x. So what is the derivative of y with respect to x? You can write it as y prime, or you can write it as dy dx. I'll write it as y prime, just remembering that dy dx is the same as y prime, because it's a little bit easier to write it. Minus, okay, here we have to do the chain rule, right? Y is a function inside the square function. So the 2 comes down, then we have y to the first power, and then times the derivative of the inside, which should be y prime. And all that is equal to the derivative of the right-hand side. Don't forget to take this derivative. It's not 8 anymore. The derivative of 8, 0. All right, so we've got 0. Okay, so now what do we do? Well, we've done the hard part, which is to say, think of y as a function of x, take the derivative of everything with respect to x, both sides. Now the second step is to say, okay, solve for y prime. All right, well, that's not too bad. We say these terms here both have a y prime. This term doesn't. So what we'll do is we'll do some slight rearranging. And we'll say, all right, these two terms we'll leave here, and we'll go ahead and factor out a y prime. So we can write this as x minus 2y times y prime. And this, let's take that across, is equal to negative y. Or we get that y prime is equal to negative y over x minus 2y. And there we go. Now, of course, you can do a few other things if you don't like y prime. Say, well, that's dy dx. And the other thing is, I don't like a negative there. You can multiply top and bottom by a minus, and you can write this as y over 2y minus x. They're both the same. They're both fine. So there's all sorts of small things you can do. But the point here is we have this wonderful expression. And it's much better than trying to solve for y. If you had to solve for y, you'd end up with a square root, because you'd have to solve a quadratic. Things would get messy, and it would turn out, at the end of the day, you don't really gain anything from that mess. This, in some sense, is actually better. It encapsulates everything. All right, so that's part A. Now part B. Find an equation for the tangent line at the point 6, 4. So the good news is we have our point. So what do we need? If we're making a line, there's always two pieces of information, right? The point and the slope. Well, the point's done. So what's the slope? And that's testing us on like, oh, yeah, derivative. Derivative is the slope of the tangent line. So we say, oh, okay, so our slope would be what we call dy dx. And then I like to write it this way, evaluated at the point 6, 4. So whenever you see a large vertical bar, it means we're going to evaluate the expression. So in this case, our expression, well, we pick one of these. Doesn't really matter which one. Well, let's pick this one. It's more positive, right? We're optimists. We like positive things. So that's going to be y over 2y minus x, evaluate at 6, 4. And so we say, okay, so wherever we see a y, we're going to put a 4. Wherever we see an x, we put a 6. So that's a 4 upstairs. Downstairs, 2 times 4 is 8 minus 6. So that's 4 over 2, which is 2. So now we have our slope. We have our point. And say, okay, our tangent line is y minus our y value, so which is 4, is equal to our slope 2, x minus our x value. Well, we can clean this up. So for example, we can say y is 2 times x. Then you have a minus 12. Then you can add 4. Minus 12 add 4 is minus 8. And we're done. That's it. That's our tangent line. All right. Great. Wonderful. And these are fun, right? And we're doing wonderful. And let's keep moving along. Number 3. Use logarithmic differentiation to compute the derivative of f of x, which is x to the 4th times x minus 3 to the power arctangent 2x over the square root of 1 plus x squared. No credit will be given for other differentiation methods. Well, to be honest with you, this is a problem where you have to do logarithmic differentiation. So yeah, of course we're not going to get any credit for other methods because other methods are bound to fail. Your answer should be a function of x alone. Do not simplify your answer. Oh, bonus, we don't have to simplify. Now, when it comes to logarithmic differentiation, there are sort of two schools of thought. And what are they? Well, one school of thought is to say, all right, you have y equals a crazy expression, f of x. And you say, well, this involves lots of multiplying, functions both upstairs and downstairs kind of thing going on. I mean, something like this, x minus 3 to the arctangent 2x. And so what you say is, you say, all right, log of y equals log of f of x, and log is this beautiful thing which helps you pull apart anything that involves lots of multiplying. And you use that to rewrite your expression, you clean things up, you separate. That separation allows us to do an easy differentiation, and life is good. And so we say, okay, now take derivatives after you use your logs, and life is great. And we end up with here a 1 over y prime equals stuff. Then you multiply both sides by y, which is f of x. Now, that's one school of thought. It works great. I just remember it in the following way. So the way I remember logarithmic differentiation is to say, oh, log of, the derivative of f of x is equal to f of x times the derivative of the natural log of f of x. And so this is my way to think about logarithmic differentiation. It's actually the exact same. All right, so that's the key. If we can remember that, this problem is great. It's going to flow like honey. Well, maybe warmed up honey. So here we go. So we have our derivative. We'll go ahead and write that as f prime of x is equal to, so according to this, it's our original function. So we have to write all that again. So x to the fourth, x minus 3, arctangent of 2x, over square root of 1 plus x squared, times the derivative of the natural log of x to the fourth, x minus 3, arctangent of 2x, over the square root 1 plus x squared. All right, so the key here is to know your properties of logs. So what are they? Well, there's a couple of them. Log of a times b is equal to log of a plus log of b. So in other words, multiplication becomes addition. Log of a over b is equal to log of a subtract log of b. So that says that division becomes subtraction. And then the other one is log of a to the b is b log of a. That says exponents come down. All right, well, now that we have these three properties, we can start breaking up. Now you can do it in several steps, or if you're comfortable, you can do it all at once. Now I'm comfortable, so I'm going to do it all at once, but if you're not comfortable, I encourage you to be slow, take your time. So we still have all this out in front, x to the fourth, x minus 3, arctangent of 2x, and this is one of the reasons this problem takes a while. There's a lot to write down. Square root of 1 plus x squared times the derivative. Now, everything that's multiplying on the top gets its own term. So I say, okay, derivative of log of x to the fourth. But that's x to the fourth, there's a power, so that becomes 4 log x. Go to the next term. Okay, I'm going to have this term, x minus 3 to the power arctangent 2x. But wait, there's a power. So that comes down. Arctangent of 2x, because that's the power, log x minus 3. Okay, upstairs add, downstairs subtract, because division becomes subtraction. So we're going to subtract, and it's log of the square root of 1 plus x squared. Well, that's really 1 plus x squared to the 1/2. Again, power. So we can write this as 1/2 log 1 plus x squared. All right, and now this one you're thinking, great, we're done. Ha-ha! But actually, no, because what haven't we done yet? There's been no differentiation. None. Zero. So we're like, oh, darn it. So we actually have to take derivatives now. But the point is, we've pulled things apart. And the hard thing is differentiation is when you have lots of stuff together, pulling it apart says, oh, these are all little pieces, and we know how to take the derivative of each little piece. All right, so here we go. We have, of course, the stuff in the front again. So we rewrite that one more time, and hopefully this will be our last time, because remember, they said, do not simplify your answer, so we're going to really take them at their word. Square root of 1 plus x squared. All right, now do it term by term. The derivative of 4 natural log x would be 4 times 1 over x, so that's 4 over x. Here we have a product rule. Okay, so the derivative of the first. Derivative of arctangent 2x, personal favorite of mine. I'm a big fan of arctangent. You know, if you hang out often enough with me, you're like, it's only a matter of time. Now normally it'd be 1 over 1 plus what's on the inside squared. So we write that 1 plus the inside squared. Okay, but chain rule, derivative of the inside, we put a 2 here. So that's the derivative of arctangent of 2x. Don't forget, times log of x minus 3. Plus, okay, that was the derivative of the first times the second, so plus the first, arctangent of 2x, times the derivative of the second, which would be 1 over x minus 3. So we can just put n x minus 3 downstairs. Then we say, okay, minus a half, and we have natural log of 1 plus x squared. So the nice thing about natural log is it's easy to take derivative. You say, okay, whatever's on the inside, 1 over that. So there's a 1 plus x squared. And the derivative of 1 plus x squared is 2x. And then we're done. Do we simplify? No. It tells us, don't simplify. So we're not going to do anything like cancel some 2's or anything like that. That would be simplifying. And so there we go, our derivative in all its splendiferous glory. What a fun problem. What a fun problem. Of course, the key is know, the formula for logarithmic differentiation, but equally important, know how to use logs to pull your expression apart. That's why we study logs. And if you talk to your parents or grandparents, they study logs even more than we do. It was all the rage back in the day, back before they had calculators. But that's a different story. For now, our story is we're done, and we're ready to keep moving. Number 4. An object in the shape of a cylinder has a volume of 72 pi cubic meters. That's a pretty big volume there. Its radius and height are changing in such a way that this volume remains constant. Okay, so this is something that's changing. So both radius and height are changing. It sounds like related rates kind of thing. Just we know that things are changing, and there's more than one thing changing. Just that idea. If we see more than one thing changing, related rates. All right, so what do we have? If the height is increasing at a steady rate of 5 meters per minute, find the rate of change of the radius at the moment the height is 8 meters. And include units in your answer. Now, we need to know something. What's the volume of a cylinder? And they tell us the volume is pi r squared h. Now, why do we need to know that? Well, when we think of related rates problems, the key is, what's the relationship? And so we have to figure out what the relationship is. In this case, it's given to us because it's the volume. The volume remains constant. So we say, okay, so pi r squared h, where h and r are changing, has to equal 72 pi. Or, we can cancel off a pi. We say, okay, r squared h is 72. Now, you might say, is this implicit differentiation? The answer is no. We're not going to solve for h in terms of r, or r in terms of h. We're going to think of r and h as both functions of t. So, if we were doing our little thought bubbles here, we'd say, oh, r is some function of t, and h is some function of t. So what do? Well, we take the derivative of both sides with respect to t. Okay, That's not too bad. So we'll have here product rule. Say, all right, root of r squared. Well, remember, r is a function of t. And if it helps, you can even just write down r of t squared h of t is equal to 72. So the derivative here would be 2r, all right, the 2 comes down, r to the 1, and then times r prime, and we'll write that as dr dt, just to emphasize change with respect to t, and then times h. So the derivative of the first times the second, plus r squared times the derivative of h, which is dh dt. So that's the derivative of the left-hand side with respect to t. Has to equal the derivative of the right-hand side with respect to t. Well, 72 isn't changing, so it's 0. So now we have a relationship between our rates. You say, okay, good. Related rates, we have our relationship. So we have to start thinking about, what do we know? Well, we know a couple of things. The height is increasing at a rate of 5 meters per minute. So that's dh dt is equal to 5. And we'll use our units. We'll throw them in there for the time being. Find the rate of change of the radius. At the moment, the height is 8 meters. So h is 8 meters. You might say, okay, so let's see. What do we know? We know the h. We know the dh dt. The problem is we have two things left, dr dt and r. Now, what are we after? Well, we're after the change of radius. So we're after dr dt. But what's r? Well, for that, we say, well, what do we know? We know r squared times h equals 72. So we can do a little bit of work here on the side. And we can say, okay, r squared times 8 equals 72. So at r moment, the one we care about, so we'd say, okay, so that says at the time we care about, 72 divided by 8 is 9. So our radius is 3. Now I might say, wait, Steve, plus minus. No. This is a physical object. You can't have a negative radius. It has to be the plus. Okay, so our radius is 3 meters. All right. And now we just plug in for what we know, solve for what we don't. It's a great way to do things. So we have 2 times 3 times dr dt times h plus r squared dh dt equals 0. All right. Well, if we start moving things around, what do we get? Well, we get 2 times 3 times 8 is 48 dr dt is equal, over here, 9 times 5 is 45. But move it across, negative 45. Or we could say, hey, dr dt is negative 45 over 48. Now, they both have a factor of 3. So you can write this as negative 15 over 16. And we should say, it makes sense that the value is negative. That's good. Because if both r and h were getting bigger, the volume would have to be getting bigger. But our volume has to stay the same. So whenever one is going up, the other one should be going down. Okay? So that makes sense about the sign being negative. 15 over 16 is about 1. Okay, that's fine. If we got like a really crazy answer, like 1,000,000, that would be suspicious. Are we done? I mean, we can go ahead and throw a box here, right? But is this our answer? And why is there a suspiciously big gap? And the answer is, no, we're not done. Because what are we missing? Units. Well, how do we find our units? And you might say, oh, it's going to take us a long time. But actually, it's really cool. You can read it off your notation. Because what do we have? We should have a change in r over a change in t. So we should have units of r over units of t. What's r being measured in? The answer is meters. What's t being measured in? And the answer is minutes. So minus 15/16 meters per minute. That's our rate of change for r. And we're done. Woo, nice. Fun problems, fun problems. That brings us to number 5. Find the absolute maximum and minimum values of the function f of x is minus x squared plus 4x plus 1 divided by x plus 1 on the interval from 0 to 4. So we can go about this and say, all right, what do we know? Well, we think about this. So the first thing is we know it's going to happen because we have a closed interval, which means we include the endpoints, and it's bounded, so nothing's heading off to infinity. So this is our making a list. We're making a list. We're checking it twice. We're going to find out which points are nice. And on our list, we always include the endpoints, because our absolute max and min could happen at, basically, there's 2 places. An endpoint, so we have to throw those in, and what we call a critical point, where the derivative equals 0. Now, let's take our derivative and set that equal to 0. So here we have a quotient, and so we can take the derivative and set that equal to 0. Now, I should comment, there's 2 things you could do. And we'll do the first thing, which is just like, I see a fraction, I'm going to use quotient rule, let's do quotient rule. But there's a second thing you could do, which we'll talk about in just a moment. Okay, so first thing, taking our derivative, so f prime of x, we have to just remember the rules. It's the bottom, so that's x plus 1, times the derivative of the top, which is minus 2x plus 4, and minus the top, minus x squared plus 4x plus 1, times the derivative of the bottom, which is 1. And all of that, divide that by the bottom term squared. Okay. Well, we clean that up, and what do we get? Well, okay, be careful, you got to do some multiplying. It's always dangerous. X times minus 2x is minus 2x squared, then 4x, and then a minus 2x, and a plus 4. Here, you have a minus distributed in, so make sure you get it to each term. So it would become a plus x squared, a minus 4x, and a minus 1. And all of that over x plus 1 squared. Now, we should have noted that the bottom makes us a little bit nervous, but it only really has a problem at x equals negative 1. We're not going near negative 1. Our interval 0 to 4 does not overlap negative 1, so we're fine. Okay, so we say, well, we can clean things up. Certainly we can cancel some 4x's right away without much thought. We have minus 2x squared plus x squared, which is minus x squared, and that takes care of those terms. We have the minus 2x, so that's good. And then plus 4 minus 1 makes a plus 3 over x plus 1 quantity squared. Well, we can pull out a minus just because we like to have a 1 in front of the x squared, because we've been trained to factor things in that way. And the reason I say we want to factor is, what's our goal? So our real goal is to ask the question, when does f prime of x equal 0? So that's our real goal, is we're going to set this equal to 0 and figure out what values of x that's true. Those are going to be points on our list. So we say, okay, does x squared plus 2x minus 3 factor? Probably, because, our teachers like us, and that's a great thing about math. Your teachers like you when you take math. And, okay, so how does it factor? Well, let's see, what would we have? We need 2 things that multiply to negative 3 and add to positive 2. So that would be a plus 3 and a minus 1. We can check, right? X squared, good. Minus x plus 3x, 2x, and minus 3. So set this equal to 0. This part can't make it 0, all right? So what's left? Well, we get 1 or negative 3. So what makes the list? Well, I claim 1 makes the list. Well, yeah, because 1. But what about -3? Ooh, be careful. Be careful. It's here to be, a little bit of a temptation here. Like, yes, we should add it to our list. But why not? Look at our interval. Our interval only goes from 0 to 4. Is -3 between 0 and 4? And the answer is no. So it can't be on our list. So then we're done making our list. Our list is very short, a total of 3 points. Okay, great. So now that we've made our list, we plug in. And what we do is we know our absolute max and absolute min has to occur at one of the 3 places, 0, 4, or 1. So we're going to plug them into f and see what values we get out. Now when you plug in 0, it's very easy because you get 0 plus 0 plus 1, and then you get 0 plus 1, which is 1 over 1, also known as 1. Okay, so that's not so bad. What about 4? Well, okay, that one you have to think a little bit. You get -16 plus 16 plus 1, which means you get a 1 upstairs. What about downstairs? 4 plus 1 makes 5, 1/5. Okay, well, what about 1? You're going to get a -1 plus 4 plus 1. So you're going to get a 4 upstairs. Downstairs, 1 plus 1 is 2. So you get 4 halves, also known as 2. And now you say, okay, what's the biggest number? That's your max. So the absolute max is 2, because that's the largest of the 3. And your absolute min is 1/5, because that's the smallest of the 3. And we don't need to know where it happens, right? Because you always have to be careful. Because sometimes it says find where it happens versus find what it is. Sometimes it says find both. And in this case it says find the values. So we're after these numbers, 2 and 1/5. And so there we go. That's it. We're done. Good, good. Now, I made a comment a few minutes ago that you really could have done 2 things. So the first thing is you just use the quotient rule and you just do what you would normally do when you see this problem. The other thing, of course, is to say, well, I could, and I'm not saying you need to do this, I could rewrite this. And this is getting more into kind of things you'll see in Calc 2, a foreshadow of things to come, which is to say, hey, I could take this -x squared plus 4x plus 1 and divide by x plus 1. So do some long division. You can. What would happen? Well, -x plus 1 divide into -x squared plus 4x plus 1. Because this is not really the point of the test, I don't want to spend too much time. But the rule is you work with the leading terms. So I have x. To get -x squared, I'd have a minus x. So then I'd have -x squared minus x. You subtract. And that would leave us with, well, the x squareds cancel. 4x minus x is 5x plus 1. I say, well, okay, now I have a x and a 5x. So I should add a 5. And then 5 times x plus 1 will give us 5x plus 5. And we should subtract. And we'll end up with the 5x's cancel. 1 subtract 5 is -4. Which is just a way for us to say that we could have used as our function f of x is -x plus 5 plus our remainder divided by x plus 1. And so we could have used that function from the start and worked it out. And we said, okay, well, for example, how does that help us find our critical points? Well, now when we take derivatives, they're a little bit easier, right? Because what is f prime of x? We'd see that f prime of x is -1. The 5 goes away. Here, this is x plus 1 to the -1. And so when we take a derivative, there's a minus comes down, which makes this a -4 to a plus 4. And then it becomes x plus 1 quantity squared. And if you set that equal to 0, you see, aha, what does that tell us? Well, it tells us that x plus 1, quantity squared, has to equal 4. Or it says, oh, x plus 1 has to equal plus minus 2, which says that x has to be either, well, 2 minus 1 is 1, or negative 3, which is what we already said. So you could have done this as well. It's an option. If you don't know how to do it, don't worry. You don't need to know yet. Someday. But that's just another thing that could have been done. But for now, we're happy. We got our answers. Absolute max is 2. Absolute min is a fifth. Life is good. And let's keep moving on. Number 6. Let f of x be a continuous differentiable function for negative 5 less than or equal to x less than or equal to 5. Consider the graph y equals f prime of x. So be careful here. This is not f of x, it's f prime of x. You might say, well, wait, there's this little sharp bendy point. Is that allowed? Yes. It's okay. Don't worry. No worries. All right. Use the graph to answer the following questions. And then we have various things. For each pair of values, circle the less than, equal, or less than sign. Well, that's a typo. They meant to say greater than sign. To give the relationship that exists between the values, or circle more information needed. So, we want to look at f of negative 5 versus f of negative 3. So we want to say, okay, which one of these values for f is bigger? You might say, aha, I see f of negative 3 is higher than f of negative 5, so it's f of negative 3, right? 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 But remember, gotta be careful. This is f prime. So what's going on here? What we're saying is that between negative 5 and negative 3, our derivative is negative. So from negative 5 to negative 3, our derivative is negative. Now, what does negative mean? It means our change is going down. So wherever we are at negative 5, we're going to keep going down before we get to negative 3. So in that case, if we start at negative 5 and we go down, then f of negative 5 has to be bigger than f of negative 3. So that's that circle, right? We're really caring about the signs. The signs tell us whether we go up or down. So negative, where we see negatives, function goes down. Where we see positive, function goes up. Okay, f of negative 2 and f of 0. So negative 2 is here, 0 is here. Now, of course, they're trying to say, oh, same value. No, we're not going to fall for their trick. We're negative, right? So negative says we're going down. So f of negative 2 has to be bigger than f of 0. All right, what about f of 1 versus f of 4? Well, what's happening in between 1 and 4? Our derivative is positive. So our derivative is positive means our function has to go up. If our function is going up, that means that f of 1 is smaller than f of 4. All right, last one, f of 4 versus f of 5. Well, our derivative is negative here. Well, that means we're going down. If we're going down, so if f of 4 is here, f of 5 is there, f of 4 is bigger. So this is kind of testing us on two things. You know, do we understand how the sign of the derivative tells us up or down? And can we sort of be careful and not be tempted by this picture too much? Make sure we understand that this is indeed f prime, not f. They have different characteristics. All right. Item B, because there's lots of items here. Identify the open intervals for which f of x is concave up. Now, concave up means what? Well, that means f double prime has to be positive. Okay, so that's concave up. We're happy. Okay, so f double prime is positive. Now, what does that really tell us? If f double prime is positive, that's the same as saying, oh, f prime is increasing. Oops, I don't have quite enough space, but you can imagine I had enough space to say increasing. So now come back to the picture and say, where is this increasing? Well, we're going up, so that's increasing from -5 to -3. Okay, so that makes our list, -5, -3. And then we're going down, that doesn't count. At -1, we go back to going up. Okay, so that goes from -1 to, let's see, where is that at? That looks like about 2.5. So -1 to 2.5, and then we're going down again. Okay, so that's concave up. Now, part C. When is it concave down? Well, of course, no surprise, that's f double prime less than 0. And okay, that's looks like that. And that's when f prime is decreasing. That's when we're going down. So, again, looking at our picture, we're going up, we're going down. So we're going down from -3 to -1. Okay, so let's see if we can almost fit this. Yes, we can. -3 to -1. We go back up, and then we go down again. So from 2.5 to 5. All right, last one. Identify the x values for the inflection points of f of x. Now, you can think of it in a couple of different ways, but essentially, inflection point, you could say, that's where we change concavity. In other words, going from up to down. Okay, so where do we change concavity? Well, you can think of it as our various endpoints, but you could say we change concavity at those places. Now you might notice like, oh, those look like max and mins. Yes, they do look like max and mins because they are max and mins. But they're also the places where we look at these intervals where we have things happening at -3, at -1, at 2.5. And so we have our list of points. And there we go. That's it. We're done. Beautiful. They like problems like this that test your sort of intuition because you don't know what the function is. So you have to say, well, what are the principles of the function? So make sure you understand how things relate. Derivatives and first derivatives and second derivatives. What does it mean to be concave up? What does it mean to be concave down? How does it relate to the derivative? How does it relate to the second derivative? And all these fun questions. But good times. That's number 6, right? One more. One last problem and we'll be done. Our final problem. Number 7. Determine the points on the curve y equals x squared minus a half that are closest to the point 0, 4. And justify your answer using appropriate derivative or limit computations. Okay, so what's going on here? Well, we have x squared minus a half. So that's a parabola, and it's just been shifted down ever so slightly. So here is our y equals x squared minus a half. And now we say, okay, we have the point 0, 4. X equals 0, y equals 4. And so that's there. And now what we're trying to say is, well, which points are closest? Now, just the picture is sort of indicating there's this symmetry going on. So we kind of expect there to be 2 points. And that's okay if we get 2 points at the end. Now, there is a chance that there's 1 point, which would be if the very bottom is the closest point. But I'm skeptical about that. Well, mostly because I'm an old person. I'm skeptical about everything. Okay, so how do we begin? Well, we have a word that has an ist, close-ist. So this is really optimization. And so we say, all right, so if we're doing optimization problems, what do we need to do? Well, we need to say what's the function we're trying to optimize, and then we need to take derivatives and optimize it. So what's our situation? Well, closest is a distance kind of question. So we're looking at distance. And we say, all right, well, do we know something about the distance? And they gave us this nice formula. Says, oh, yeah, there's this distance formula. And they even gave us a hint saying, square roots could be messy, so minimize the square of the distance. Oh, that's right. Because if I want to make the square root of something small, I just have to make the something on the inside small. So we say, okay, good. Now, the question, what are our points? Well, one point is obviously this 0, 4. The other point is on the curve, and that we can write as x, x squared minus a half. That's one way to write it. So x, y, but y is x squared minus a half. You can do other things, but this works for us. Say, all right, so what do we have? So our goal is to optimize our function, f of x. So we take x, subtract 0, quantity squared. All right, x subtract 0 squared, right? There's that, minus that. And add x squared minus a half, subtract 4, and again, quantity squared. There we have our optimization problem. Well, we can write that as a little bit simpler, x squared plus x squared minus 9/2 squared. Now, we don't have to expand it right now. What do we need to do? Well, we need to take our derivative and see what's going on. So let's do that. So we have f prime of x is equal to 2x plus, now here the 2 comes down, x squared minus 9/2 to the power of 1 times 2x again. Okay, well, notice we can say, hey, both these terms have a 2x involved, so we could factor that out. So we have 2x, then we have a 1, and here, what do we have? Well, we have 2x squared, and then we can multiply the 2 through, and minus 9. Or, that's really 2x times 2x squared minus 8. Well, okay, you can factor out another 2, and that makes this 4x times x squared minus 4, which is 4x, x plus 2, x minus 2. All right, now, when we're doing optimization, what do we care about? We care about where the derivative is 0, and I'm going to say it just because you have to look, endpoints. Do we have endpoints? This problem doesn't, but some problems do. And sometimes the optimization does happen at the end, so you have to be careful. And sometimes they're very sneaky, like, oh, and they put the optimization at the end, so I'll double check. But the point here is we have 3 candidates, 0, minus 2, and positive 2. All right. So, which values of x are the right values? Well, how do we figure that out? Well, what we can do is we can do some sort of a appropriate derivative computation. So what is that? Well, we can use a first derivative test or a second derivative test. And, well, we have our first derivative is actually pretty nice. So let's go ahead and just do a first derivative test. So we have 0, minus 2, and plus 2. And now we say, okay, look at the signs. So let's plug in. So for example, if you plug in a 1, you get a positive, and, minus 1. Negative, right? 4 times minus 1 is negative. Positive and negative, which means our f prime is positive. If you plug in positive 1, then you get a positive, and negative. f prime is negative. Plug in 1,000,000 or 3, they're about the same. Positive, 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 so f prime is positive. Plug in, say, negative 3, negative, 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 f prime is negative, which means we're going down, then up, then down, and back up. So our minimums, our candidate minimums, are going to occur at x equals plus minus 2. And we're just going to say we did the first derivative test. Just so if they ever ask, did you do a test? We did. We did a derivative computation. Now, which one is it? Well, we have the symmetry. And so we say, great. And it makes sense, right? Because what's happening is you can be very far away, you get closer, and then you get farther away, get closer again, and farther away. So we are almost there. We want to be careful, though, that we answer it in the way they asked us to give them the answer. So how did they ask us to give an answer? They want points, not x values, points. So, and there's 2 of them. So we'd have 2, and then we'd have 2 squared, which is 4, minus a half. All right, well, 4 minus a half, that's 8 halves, so that would be 7 halves. Comma, negative 2, and again, 4 minus a half is 7 halves. And so those are the 2 points which are nearest to 0, 4. And they didn't ask us to say what's the distance, so we don't need to find it. They just said, what are the points? So we're good. Life is good. Another test done, some knowledge gained, and we're learning. We're doing great. I hope you do well. I hope you pass it, and you walk out of that test head held high, and because like, I know this. I believe in you. You're going to do great. So do great. And we'll see you again. Bye.